So now that we've seen a handful of different Maclaurin series representations of functions, let's take a look at some of the important ones that we've seen so far. We have some of these that we adapted from this function 1 over 1 minus x. For instance, we developed the formula for tan inverse and for ln of 1 plus x using that series. So the corresponding radii of convergence are all 1 for those. And we also saw for the functions e to the x, sine x, and cosine x, we were able to derive those directly from our Taylor series formula. And we also showed that for each of those that they converge for all real numbers, so their radii of convergence will be infinity. And then the last one we saw was the binomial series here. And that one was convergent on a radius of on an interval with a radius of convergence with r equal to 1. So let's see what can we do with some of these known Taylor series, known Maclaurin series, in a way that might help us compute certain things that involve these series. For instance, suppose I want to find the sum of this series, 1 over 1 times 2 minus 1 over 2 times 2 squared, plus 1 over 3 times 2 cubed, minus 1 over 4 times 2 to the 4th, and so on. What is this series? Well, it's the series 1 over n times 2 to the n, and actually here starting with n equals 1. So what we can try and do to find the sum of this series is try and see what function can be represented by this series, and then what value is that function being evaluated in this series. So to remind you, we have a few options here. So I'm going to flip back to the previous slide and we can try and find one that matches this form here. So we're looking for one that's in the form with n in the denominator. So I notice here that the ln of 1 plus x formula seems to match it pretty well. Okay. Oh, and one thing I forgot to mention here is that they're alternating. So this should be negative 1 to the n over 2 to the n. Okay, so if we remember here for ln of 1 plus x, it has a series of the form negative 1 to the n, x to the n over n. Okay, so again here to remind you, this is where that one came from. And actually, yeah, it should start with negative 1 to the n minus 1 because it starts with a positive term. Okay. And why am I using this? Well, notice that essentially it's the same series here. It's got the negative 1 to the n minus 1. It's got that part there. And it's got the n in the denominator. It's got that part there. And instead of x to the n, it's like it has 1/2 to the n. Right? Because you notice it's got 2 to the n in the denominator. Well, that's the same as 1/2 to the n. So you notice that this is really the same as ln of 1 plus x, but evaluated at x equals 1/2. So notice that if I do 1 plus 1/2 here, we get exactly that series. So therefore this series will sum to ln of 3/2. So we were able to find the sum of this series by recognizing that it's the Taylor series of 1 plus x, evaluated at x equals 1/2. Here's another example of how we can use Taylor series. Suppose I want to integrate the function e to the negative x squared as an infinite series. Remember, this is a function whose antiderivative is not an elementary function. So we couldn't express this integral as an elementary function, but we can express it as an infinite series. So let's start by trying to find the Taylor series of e to the negative x squared. So we know the Taylor series of e to the x is the series x to the n over n factorial. Right? So just to write out a few terms here. E to the negative x squared, I can get the Taylor series for this just by substituting negative x squared in for x. So in this case, it would be the series negative 1 to the n, x to the 2n over n factorial. So the terms would be 1 minus x squared plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial, and so on. So now if I want to integrate e to the negative x squared, I can just do term-by-term integration of this series. Okay, so we can take the integral of x to the 2n in the formula for the series. So I'll write c plus sum negative 1 to the n x to the 2n plus 1 over n factorial times 2n plus 1. Okay. So you see all we're doing is really just taking the integral of each separate term of the series here to form this series. Okay, so we can even just write out some of those terms here. So that's how we can do the integral of e to the negative x squared. Notice it's not written as an elementary function in this case, it's written as a power series. So now if I wanted to numerically evaluate this integral, I can evaluate the terms of the series. So putting in values of x into the series allows me to approximate this integral. Here's another example. Suppose I want to evaluate the limit as x goes to 0, e to the x minus 1 minus x over x squared. Well, of course we know that we have some methods for dealing with these types of limits where it's in the form 0 over 0, because you can use L'Hopital's rule. But for the sake of demonstrating how we can also use Taylor series to do things like this, I'm going to try and write e to the x as a Taylor series, or as its Maclaurin series. So we know its Maclaurin series would just be 1 plus x squared over 2 factorial, x cubed over 3 factorial, x to the 4th over 4 factorial, and so on. Okay, so I'm just rewriting e to the x like that as its Taylor series. And then the next two terms, minus 1 minus x, we can then combine with these terms here in the series. So subtracting minus 1, we get that term goes, and minus x, this term goes. And then the remaining terms can all be divided by x squared. Right? So if I divide each of these terms by x squared, we can cancel out the x squared from there, so that's just 1 over 2 factorial. X cubed divided by x squared will just be x over 3 factorial. X to the fourth divided by x squared will be x squared over 4 factorial. And so I notice that the remaining terms will all have a factor of x in the numerator. So now, as I take the limit as x approaches 0, these will all become 0. So all the terms from there on will be going to 0 as x approaches 0. So we're just left with 1 over 2 factorial, which is 1/2. Okay. Notice here we didn't have to use L'Hopital's rule, but instead writing out the terms of the Taylor series of e to the x allowed us to simplify the limit into a form that we could evaluate. And one last thing here I want to show you is how we can combine Taylor series through multiplication or through division. And the first example here, we want to find the first 3 non-zero terms of the Maclaurin series for e to the x sine x. So we know a Taylor series for each of them. So let's just write out the first few terms so that we can do a little bit of distribution between those first few terms. So e to the x, we know that's 1 plus x squared over 2 factorial, x cubed over 3 factorial, and so on. Sine x we know is essentially all the odd power terms here, but alternating in sign. So it's x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on. So what I'll do is I'll just do a little bit of distribution to get the first, in this case we just want the first 3 non-zero terms. So we want the lowest degree terms. So I'm going to start with 1 distributed here to get some x cubed terms, and then we'll distribute the x here. And then if I need to go higher than that, we can go a little bit further. But let's just distribute what we have there. So that'll be x, x cubed over 3 factorial. Okay, and then of course there would be more higher degree terms after that. Now let's distribute x, so that would be x squared minus x to the 5th over 3 factorial. So x to the 4th, x times x cubed will be x to the 4th over 3 factorial. And then some higher degree terms. Notice then here, if I were to do the next one here, x squared times these guys, what would I get? I would have x to the 3rd over 2 factorial, and then x to the 5th over 5 factorial. Sorry, x to the 5th over 2 times 3 factorial. Okay, anyways, so we probably don't need to go up to the 5th degree term. Since we're only doing the first 3 non-zero terms, I'll probably only need to go up to the x squared or x cubed term. In fact, I see here then we've got an x cubed, x squared, x cubed, so we'll go out to the x cubed term. So it'll be x plus x squared, and then here we have minus x cubed over 3 factorial, which is 6, x cubed over 2 factorial, which is 2. So we'll have 1/2 minus 1/3, or 1/6, which will be 1/3. And then a bunch of higher degree terms. Okay, so they're just kind of distributing out the first few lower degree terms. We get the first 3 non-zero terms of the Taylor series of e to the x sine x. Let's see if we can do something similar for tan x. So tan x would be dividing sine over cosine. So we can divide the series of sine x, which is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial and so on. And then dividing that by cosine, which starts with 1. Okay, and then it's x squared over 2 factorial plus x to the 4th over 4 factorial, and so on. So if we do a little bit of long division here, we can sort of guess what the lower degree terms of this expansion would be. So let's just write out what we think the long division might look like here. So I'll write 3 factorial is 6, and then x to the 5th over 5 factorial, which is 120. And then here it was 1 minus x squared over 2 plus x to the 4th over 4 factorial, which is 24. So if I do long division here, I know that when I do x divided by 1, that'll be x. And then x times these terms here, let's write it out below, would be x minus x cubed over 2 plus x to the 4th over 24. And then subtracting from above, those would keep going, by the way. We have the difference here, negative x cubed over 6 minus negative x cubed over 2, so that's a plus. Let's see, so that would be 1/2 minus 1/6 would be 1/3. So we're left with x cubed over 3. And then here, let's see, we would have x to the 5th over 120 minus x to the 4th over 24. So I think that would be minus 4, and this should be x to the 5th, by the way, 4x to the 5th over 120. And yeah, there would be more terms after that. But then we can divide x cubed over 3 divided by 1, again, would be x cubed over 3. And then multiplying here. So we would have x to the 5th over 6. And then x to the 7th over 3 times 24, 92, and so on. Again, subtracting there from above, we would have here x to the 3rd minus x to the 3rd, those are gone, minus 4x to the 5th over 120 plus x to the 5th over 6. Let's see, what would that reduce to? I think, let's see, so let me make sure I'm not making a mistake here. 4x to the 5th over 120 reduces to 4 over 120 reduces to 1 over 30. And then we're going to add x to the 5th over 6. So we would have a common denominator, make that 5 over 30 minus 1 over 30, so that would be 4 over 30. Okay, and then some higher degree terms, but that's the last one we need. So the next term there would be 4x to the 5th over 30, or in other words, 2x to the 5th over 15, and those would be the first three non-zero terms. Okay, so that's a little bit of a pain, but of course you can see that you can continue doing this process to generate more and more terms if you need to. But hopefully we don't necessarily need to do this unless I just need only a couple terms of the series.